discuss about ionospheric propagation today. Before going to ionospheric propagation, let me tell you something about why we need to discuss this ionospheric propagation and what are the other propagation methods. Like there is something called ground wave propagation, there is sky wave propagation, etc. What happens is radio wave, when it propagates, it can use different natural resources like the sea. So sea water, it has a conductivity, so it can use sea. It can use the surface of the earth. It can use the atmosphere around it, around the earth. So all these can be used, all these are useful in radio wave propagation. As you know, radio wave, which is a form of electromagnetic wave. So when we use the electromagnetic wave for radio propagation for the purpose of radio, then we call it radio wave. So this can be used, radio wave can use different resources, natural resources, as I told you now, the atmosphere around the earth, the surface of the earth, or the sea water. All this can be used by radio wave when we are using radio wave for communication purpose. For details about this, and you can see different websites. I'll give you 2-3 websites. These are the websites that you can look for details about radio wave propagation. These are some YouTube channels which gives you some knowledge, basic knowledge, or some information, basic information, although not in-depth scientific information, but basic information you can get on YouTube channel. This is one channel, this is another channel, and this is another channel. These 3 channels give you a sufficient basic understanding of how radio wave propagates. So I will ask you, or I will tell you that try to visit these channels and try to understand how radio wave propagates. Now coming back to what we are concerned today is the ionospheric propagation. Now ionosphere is a part of our atmosphere. The atmosphere that extends from the surface of the earth to about 4,000 kilometers above it consists of different types of gases. So various gases are there in the atmosphere. It starts from the surface of the earth and goes up. As it goes up near the surface of the earth or at the surface of the earth, the density of the ionosphere is high. As it goes up at about 3,000, 4,000 kilometers, its density is very low. As you go up, the density decreases. As we come down towards the earth's surface, the density increases. In this zone, the region between 90 kilometer to about 1500 kilometer or 1000 kilometer in the ionosphere, in the atmosphere, is called the ionosphere. This is called ionosphere because this region is highly ionized. Since it is highly ionized, this region is usually used in the radio wave propagation. this ionized region is used in the radio wave propagation. It has high density because of ionization. It has high density of free electrons which are negatively charged and positively charged ions. From where these ions will come, that we'll discuss later. But positively charged ions and free electrons which are negatively charged, these are the constituent of this region. These charges, they serve important effects on electromagnetic propagation. Therefore, since they are going to affect the electromagnetic propagation, we use this region for radio wave propagation. Now, let us see how this ionosphere is formed. You know, Earth gets energy from Sun. So we have Sun. From Sun, the radiation, electromagnetic radiation is coming in all directions. Let us see, our concern is towards Earth. So the radiation that is coming towards Earth, let me show you in picture that. So this radiation, when it comes towards Earth, it has to pass through the ionosphere which is surrounding the atmosphere which is surrounding the Earth, then it will reach the Earth's surface. Now when it first meets the atmosphere which is enclosing the Earth or which is surrounding the Earth, at that point on the atmosphere, the density is low, density of different gases is low. But the intensity of radiation or the energy in the radiation is maximum there because it is nearer to Sun compared to the surface of the Earth. Now, as it penetrates through the atmosphere, the density of gases in the atmosphere keeps on increasing, whereas the distance from the Sun keeps on increasing also. Since the distance from the Sun keeps on increasing, the intensity keeps on decreasing. Besides that, these gases are getting energized due to the electromagnetic wave from the Sun. So since they are energized, they are absorbing some amount of electromagnetic wave, some amount of electromagnetic energy. So some loss is there from the original radiation. As it comes to the surface of the Earth, the energy or the intensity that reaches the surface of the Earth will be minimum compared to the energy that is at the surface of the atmosphere. Why it will be minimum at the surface of the Earth? The reason is simple. It is at the farthest distance from the Sun or between Sun and Earth compared to the atmosphere. Therefore, at the surface of the Earth, it will be minimum. The energy is minimum, but density is maximum. Density of gases is maximum. Now, in the process, what happens is, at the surface of Earth, we have minimum energy. Since we have minimum energy, although there is highly dense atmosphere or the highly dense gas, because the energy is not sufficient, those gases cannot be ionized. At the surface of the atmosphere, although there is maximum amount of energy from the Sun, but that portion due to minimum amount of gas, so low density, completely low density gas, so there is not sufficient gas to be ionized. So that portion cannot be ionized properly. But in these two regions, between these two regions, there will be a region which has sufficient amount of energy and sufficient amount of density. So that region where we have sufficient amount of energy and sufficient amount of density, that region will get ionized. So in that region, the gases present in the atmosphere in that region gets ionized. So that region or that zone which gets ionized is called the ionosphere. This ionosphere is 90 kilometers above the Earth, and it extends from that point to up to about 1500 kilometers above the Earth. That is the region in which it gets ionized. Now in this ionized region, from the bottom of the ionized region to the top of the ionized region, as we move at the bottom of the ionized region, the density is maximum. At the top of the ionized region, the density is minimum in the ionized region. Now let us assume that the density, volumetric density, let us assume that the volumetric density is Ne. N is the number of Ne. Ne is the number of number of ionized particle per unit volume. Now by ionization, what will happen? By ionization, what happens is the gas absorbs sufficient of energy, so it gets energized, and the electron in the outermost orbit of the gas molecule, that will get detached from the gas molecule. Since it gets detached, electron becomes free, so we have got a free electron because of the absorption of energy. Since one electron gets detached, so the gas becomes ionized, the remaining particle becomes ionized. So that will be positively charged, the detached electron will be negatively charged. But compared to the electron, the molecule that is ionized is heavier in nature. So since electron will have less weight, the ionized molecule will have more weight. Therefore, the ionized molecule will be almost in the bound state, it will not move, whereas electrons will be free to move in the ionosphere, in the ionized medium, or in the ionosphere. Now this ionosphere is a particular type of electrical medium in which we have charged particles, we have electrons, and we have positive molecules. Since it is a particular type of electrical medium, there can be polarization, electrical polarization. Remember, electrical polarization, when I say electrical polarization, it means the medium is polarized. That we discussed about dielectric polarization. Medium behaves like a dielectric and it behaves polarized. Okay. Now, the variation in electron density, as I told you, the electron density will be maximum at the lower part of the ionosphere and minimum at the upper part of the ionosphere. This variation of electron density, this causes the waves and going from the Earth, radio waves going from the Earth towards the ionosphere to bend back and come back to the Earth. This variation of electron density that results in bending back the radio waves towards the Earth under certain conditions. The conditions are it must satisfy a condition on frequency, and it must satisfy a condition on angle of incidence. So based on a specific frequency and angle criteria, if these two conditions are satisfied, then the wave can come back, and the radio wave can come back to the Earth, which means the ionosphere will reflect back the radio wave towards the Earth. From Earth's surface, we incident an electromagnetic wave or a radio wave towards the ionosphere, and under certain conditions, under suitable conditions, the radio wave will be bent back towards the Earth. So since it will be transmitted from Earth and it will be received on the Earth's surface, therefore it helps us in establishing communication. Communication involves two things, transmission and reception. Since the wave is transmitted and received because of the bending back, it helps us in establishing communication. So this is the basic introduction to ionospheric propagation. Now let us look at the electronic density or electronic density profile of the ionosphere. Now you can see I am showing you a figure or a graph in which on the x-axis we have the electron concentration Ne, which is number of electrons per cubic centimeter, and on the y-axis we have the height from the Earth in kilometers. So the height from the Earth or the distance of the ionosphere from the Earth in kilometers is given here. Now in this you can see there are two clear boundaries. One boundary is for day, one boundary is for night. Now why these two boundaries will be there? There are two different boundaries, one for day, one for night. Why there can be two boundaries? That is a question that many times people ask. The reason is very simple, extremely simple reason. In the daytime the sun is present, in the night sun is not present. In the night, then from where will we get energy in the night? Because in the daytime sun is present, we get sufficient energy in the daytime. That energy is consumed during the night time also. So some amount of that energy will be consumed in the night time. So although you are not getting any energy, but we are consuming energy, therefore energy will decrease, ionization will decrease. So you can see the height of the ionization, height of the thickness of the ionized layer is lower in night, higher in daytime. Now we can, based on this, we can divide the layer into different, divide the ionosphere into different layers. Like the lowest layer, which is closest to the Earth, is called the D layer. Above that we call the E layer. Above that there is F layer. F layer is split into two parts in the daytime. So F1 layer and F2 layer, those two parts will merge together, giving us one layer in the night, which is called F layer. Now if you look at this, at the top you can see a region which is bent like knee. That is called the knee region. In this region, the boundary of the ionosphere for day and night, the difference between the day and night is the maximum in the knee region, which is the maximum at the maximum height. At about maximum height, there is a region where the difference between these two is maximum. Otherwise, we look at the outer ionospheric region, height of the outer ionospheric region. So this is about the distribution or about the ionosphere, how the ionosphere looks. Now, on the electron density on the ionosphere, it will vary with different conditions. First is from where on the surface of the Earth we are measuring it. Is it from the equator? Is it from the pole or any other place between equator and pole? So it is dependent on the location of the Earth. Then at what time of the day we are measuring it? If it is in the night, it will be minimum. If it is in the midday, it will be maximum. Between morning to midday, it will gradually increase. From midday to evening, it will gradually decrease to the midnight. So it depends on the time of the day when we are measuring it. Then what is the time of the year that we are measuring? In the winter season, it will be minimum because it is cold. In the summer season, it is hot, so it will be maximum. So it will be density will be maximum in the summer season, minimum in the winter season. Then the sunspot activities. So if there are activities in the sun, sunspot activities means there are some defects occur on the sun regularly on regular basis. So if they happen when there is an effect, at that time sun radiates maximum energy because of the effect, because of the defect. From that point where the defect has occurred, maximum energy burst will come out. So when there is a sunspot activity, there will be energy, high density energy, high density electron because of higher energy. So this is what it is. Then what is the layer? Layer we have just discussed. Layer is the region around the peaks in the density. The regions around peaks in the density, these are called the layer. And a flare, as I told you, in the night we get a flare. Daytime it splits into F1 and F2 layers. Then this ionosphere is also called plasma. Why? A plasma is, by definition, is a charged gaseous region. It's called plasma. The definition of plasma is charged gaseous region. It's called plasma. Now, since we have a charged gaseous region, the ionosphere is a charged gaseous region. So the ionosphere can be called as a plasma also. So plasmonic activities will occur in the ionosphere. When we apply electric field to a plasma or to a charged region, then charges in the ionosphere will get accelerated. They will be oriented along the field. Now we know the mass of the ions, which are the positive charge, is much greater than the electrons. So therefore, the motion of the ionosphere can be neglected compared to the motion of the electrons. So we consider for polarization of this plasma medium, we consider the polarization vector with respect to the electrons instead of with respect to the positively charged ions. So positively charged ions we will neglect from this point onward. We will consider the free electrons. The polarization vector, as we have already discussed, P is equal to Ne into little p. What is little p? It is the polarization. Polarization is E into D. D is the separation, average separation between the electron and the positively charged ion. So that the average separation between the electron and positively charged ion is D. Then polarization vector P is equal to minus Ne, Ne being the density. So density into P, so into polarization. So dipole polarization P, little p. So minus Ne into P, that you can write as minus Ne into E. P is defined as E into D. So it is E into D, dipole moment. Okay. Now Ne is the electron density per meter cube. E is the charge of electron, which is 1.59 into 10 to the power minus 19 coulombs. D is the average displacement vector between positive and negative charges. Then we define relative dielectric constant. As you know, the relationship between D and E is D is equal to epsilon E. Epsilon is epsilon 0 into epsilon R. Therefore, D is equal to epsilon 0 into epsilon R into E, from which we can say epsilon R is equal to D by epsilon 0 into E. So, relative dielectric constant epsilon R is equal to D by epsilon 0 into E. Then D, in terms of polarization vector, we can write D is equal to E plus epsilon 0 E. So D is equal to epsilon 0 E plus P divided by epsilon 0 E. So E epsilon R is equal to D by epsilon 0 E. D is equal to epsilon 0 E plus P. So epsilon R is equal to epsilon 0 E plus P by epsilon 0 E. That we can write as 1 plus P by epsilon 0 into E. So this will be the relative dielectric constant. Then propagation constant in the medium is gamma, which is called, for propagation it has to be real. It has to be imaginary, so that we can write as gamma is equal to jkc, kc being the wave number, you call it critical wave number or cutoff wave number. So gamma is equal to jkc. Kc by definition is equal to omega upon c into root over of epsilon r. Omega upon c is k0, k0 being the wave number in the free space. So gamma is equal to j k0 into root over of epsilon r. As you know, root over of epsilon r is equal to n, the refractive index. Therefore, propagation constant is equal to j k0 into n. N is equal to root over of epsilon r is the index of refraction. Now, epsilon r can be complex in nature. If epsilon r is complex, then its root over will also be complex. Therefore, both epsilon r and n, both of them can be complex. So dielectric constant and index of refraction can be complex in nature. In that case, we can represent epsilon r as epsilon r dash minus j epsilon r double dash. That is epsilon r. The imaginary part is responsible for loss. Similarly, n can be represented as n dash minus j and n double dash. Now, as I told you, in the plasma region is a gaseous region, charged gaseous region, and in the charged gaseous region, the electrons will be in motion, in random motion, and you have already studied in the chemistry or in physics, both in physics or chemistry, you have studied about gas laws, in which you have seen the equation of motion for a gas. The equation of motion is mx double dot x double dot means and dx square dx square by dt square. Dot means dx by dt. So it is mx double dot, which x being the displacement, mx double dot by mx double dot is m into acceleration. X dot will be velocity. Mx double dot is the acceleration. So m into x double dot. So that is m mass into acceleration plus nu m x dot. So nu is the collision frequency among the electrons as they are moving. M into x dot the velocity. So it is mx double dot plus nu mx dot. So nu mx dot, that gives the force. Mx double dot is the force due to acceleration. Nu mx dot is force due to collision. So total force is mx double dot plus nu mx dot. That is the total force. But we assume here, we have make an assumption. The assumption is the gas particles or the electrons are moving only in the positive direction, not the radio wave. Remember, radio wave is not moving in positive x direction. It is the electrons which are moving in the x direction. So then the total force is equal to minus E into Ex into exponential j omega t. From where we get this? This comes from Coulomb's law. As you know, from Coulomb's law, F is equal to Q into E. Now Q here is the charge. Charge is minus E, charge of the electron, since we are considering motion of electron. Therefore, charge is minus E. So Q is minus E. Then electric intensity. Here we have the electric field moving in x direction. So that will be the amplitude will be Ex. Time variation is for time harmonic case, it will be exponential j omega t. So now we have got a second order differential equation, linear second order differential equation. We have to solve this. Now in this equation, m is the mass of the electron. So that will be 9 into 10 power minus 31 kg. Nu is called the collision frequency. So nu is the frequency of collision among two electrons. Then the solution of this differential equation is simple. X will be equal to A into exponential j omega t. A is a constant. We have to find out what is A. So to find out A, what we will do is put this value of X in the equation. So we will find out what is X double dot. X double dot will be minus A omega square exponential j omega t. Similarly, X dot will be minus j omega into A exponential j omega t. If we put those values, then the equation of motion gives us m into minus A omega square exponential j omega t plus mu m into j omega A exponential j omega t is equal to total force, which is E into Ex into exponential j omega t. From both sides, let us cancel out exponential j omega t. Then from the left side we take A common, and we'll keep A on the left side, divide the rest of the thing on the right hand side. So that will give us A, this constant value we get now. A is equal to a little e, charge of the electron, into Ex, applied electric field in the x direction, divided by m into omega square into 1 minus j mu by omega. So this is for A. So this is the form of the solution. Using this form of the solution, now we'll look at what is the polarization vector. Polarization vector expression we have already seen is equal to minus Ne into Ex, because d here we are taking the electron motion is in the x direction. Therefore, d is equal to x. So minus NE into E into X. And now that we can write as minus NE into E. For X we write A into exponential j omega t into X cap. X cap will drop. We will consider only the amplitude part. So we'll put the drop the X cap. And what we are doing here is we are using D is equal to X cap. Now let us drop X cap to consider only the amplitude part of the polarization vector. So that will be equal to minus N E square E X exponential j omega t divided by m omega square into 1 minus j nu by omega. This looks little bit complicated, so to simplify this, we will define something called the plasma frequency omega p. If we define plasma frequency omega p as n e into e square divided by m into epsilon 0 square. Let us divide this as the plasma frequency. Then how we define a constant k, which is omega p by omega. Then we define a constant z as nu by omega. So we define these three things. Plasma frequency omega p, which is equal to root over of Ne into e square by m epsilon 0. X is equal to omega p by omega square, and z is equal to nu by omega. Using these three constants, the polarization vector P now simplifies to this form. P will be equal to epsilon 0 into Ex into exponential j omega t into X cap into X by 1 minus Jz. So this will be the expression for polarization vector. So now once we know the expression for polarization vector, we have to find out what are the dielectric constants of the plasma. So the dielectric constant epsilon r is equal to epsilon r dash minus j epsilon r double dash. And epsilon r is equal to n square, as n is equal to root over of epsilon r. So epsilon r is equal to n square. Now this we can write as epsilon r is equal to 1 minus x by 1 minus jz. This is simple since we know what is the expression for p. Using the expression for p and the expression for epsilon r, that expression we have already seen. So using that, which is 1 minus p by epsilon 0 into epsilon e, using that expression. Sorry, 1 plus p by epsilon 0 epsilon e. Using that expression, we can get epsilon r is equal to 1 minus x by 1 minus jz. So that we can now put the values of x and z. So this will give us, this is equal to 1 minus omega p square divided by omega into omega minus j. Now that we can compare with the expression for the relative dielectric constant in a conducting medium. In a conducting medium, epsilon r is equal to epsilon r dash minus j sigma by omega epsilon 0. So if you compare these two expressions for epsilon r, we can find out what is the equivalent conductivity. Epsilon r dash remains as it is. Then epsilon r dash here will be, comparing these two, epsilon r dash will be 1 minus Ne into E square divided by epsilon 0 m into nu square plus m square, and sigma will be Ne into E square into nu divided by m into nu square plus omega square. So epsilon r dash and sigma values we have got for the plasma medium. Then we will consider a special case. The special case is there is no collision. If there is no collision in the plasma medium or in the ionosphere, there is no collision, then the collision frequency will be 0. So nu is equal to 0. Put nu is equal to 0 in these expressions. If we put nu is equal to 0 in these expressions, Kc or the critical parameter, critical wave number Kc will be equal to omega into root over of mu 0 epsilon 0 epsilon r, because omega by c is equal to 1 by root over of mu 0 epsilon 0, so that we can. So Kc is equal to omega root over of mu 0 epsilon r into epsilon 0. So that will be equal to K0, which is omega root over of mu 0 epsilon 0 into root over of epsilon r. Root over of epsilon r is equal to, when you put nu is equal to 0, root over of epsilon r is equal to root over of 1 minus omega p square by omega square. So this is for no collision, collisionless case. So this gives you expression for Kc. Once we know what is the expression for Kc, then we will find out different conditions. Now, on the first condition is omega is greater than omega p. If omega is greater than omega p, omega means operating frequency or the frequency that we are using in the radio wave, frequency of the radio wave that is propagating towards the ionosphere. That is the frequency omega. And omega p is called the plasma frequency that we have defined already. So when omega is greater than omega p, then Kc is real. If Kc is real, then exponential minus j Kc z is also a propagating factor. So it is propagating wave. This represents a propagating wave. Exponential minus j Kc z represents a propagating wave, which means the ionosphere, through the ionosphere, the wave will propagate. The radio wave will propagate through the ionosphere because it gives a propagating wave. When omega is greater than omega p, it gives us a propagating wave. So the radio wave will propagate through the ionosphere. What we are doing is we are considering all this, but one effect we are neglecting in this case. The effect is that of the Earth's magnetic field. We are neglecting the effect of Earth's magnetic field. This will occur at plasma frequency that we will discuss later. Our effect of Earth's magnetic field we will consider later. Okay. Now, when omega is less than omega p, if omega is less than omega p, then Kc will be imaginary because Kc is equal to root over of 1 minus omega p square by omega square. Now omega p square by omega square will be greater than 1. Therefore, Kc will be less than root over of a negative quantity. So Kc will be imaginary. If Kc is imaginary, then exponential minus j Kc z will be equal to exponential minus absolute of Kc into j, which means it is a exponentially decreasing function. So if this term is exponentially decreasing function, Kc is going to be give us an evanescent wave or a non-propagating. So as long as omega is less than omega p, the radio frequency of the radio wave is less than omega p, the radio wave cannot pass through the ionosphere. The ionosphere will block the radio wave because it cannot propagate through the ionosphere. It will be blocked by the ionosphere. The radio wave will be blocked by the ionosphere and it will come back towards the surface of the Earth. Now the third condition is, third special condition is omega is equal to omega p. When omega is equal to omega p, Kc is equal to 0. This occurs at what we call the critical frequency Fc. So Kc is equal to 0. Kc is equal to, we know, 1 root over of 1 minus omega p by omega p square by omega square. So that is equal to 0, means 1 minus omega p square by omega square is equal to 0, or omega p square is equal to omega square. From that we can find out what is omega p. So what is the value of omega in terms of omega p? Omega is equal to, from that we will get omega. From omega we will get what is f. So that will give us the f, or the critical frequency, which is called the plasma frequency also. Fc is equal to 9 root over of Ne max. Ne max is the maximum density. So 9 comes from root over of 81. Actually, if we put the value of epsilon 0, E and M, so that will give us Fc is equal to root over of 81 Ne max. Now, root over of 81 is 9, therefore Fc will be approximately equal to 9 root over of Ne max, putting those values. This is called the critical frequency. At the critical frequency, the wave gets reflected back towards the Earth. Remember that omega c, or Fc, this depends on the altitude, because the electron density is a function of the altitude. So from which altitude we are sending the radio wave, that will decide this Fc. That is one factor. Now for electrons, the highest frequency at which the reflection occurs is Fc, which is the reflection at normal incidence. So if you make a normal incidence, the highest frequency for which the reflection occurs is called the critical frequency. Fc, the critical frequency, is the highest frequency for which reflection occurs when we make a normal incident towards the ionosphere. Remember this. This is the definition of critical frequency. Critical frequency is the highest frequency for which reflection occurs from the ionosphere for a normal incident of the radio wave, and this requires the largest Ne, or the highest Ne, highest density. The point from which the reflection will occur is the point where we have the largest Ne. Now look at this, the Earth, we have got the Earth. On the Earth we have got the ionospheric layer. So ionosphere, we can see the band which shows us the ionosphere. In the ionosphere, from different points the reflection can occur. So corresponding to different frequencies, from different points the reflection can occur. When omega is equal to omega c, epsilon is equal to epsilon r, and at that point the reflection will occur from a height where Ne max is there. Ne max, or the density, is the maximum, and that height is also called the virtual height. So you transmit a wave vertically upward, but transmit a wave, radio wave, from the surface of the Earth vertically upward. It will go into the ionosphere up to certain distance. When it meets Ne max, it will get reflected back towards the Earth. So when it comes back towards the Earth from a height, that height from the surface of the Earth is called the virtual height. H dash is called the virtual height. So H dash is the height from which the reflection occurs, or the reflection where the reflection point occurs. That point is called the distance from the surface of the Earth to the point from where reflection occurs for a vertical incidence onto the ionosphere is called the virtual height. We'll stop here for today. We have discussed about what is ionosphere, what is polarization in the ionosphere, and what is the expression for dielectric constant in the ionosphere or in plasma, and all these things under the assumption that the Earth's magnetic field is not playing any role. So we'll consider that later, but up to now we consider this. From that we found out what is critical frequency, what is plasma frequency, and what is the height, virtual height. All these things we have found out for today, from today's discussion. So this will stop here. Thank you. If you have questions, etc., you can ask me. Chrome. Second.